Swayam Prabha. Digital India. Educated India.
We have been solving problems on rigid body rotation, and the way we have gone about it is, first we considered fixed axis rotation and then rotation about some sort of a symmetry axis, and finally we have talked about rotation in 3 dimensions where omega has all 3 components and the axis of rotation is not necessarily principal axis. In this lecture, which is the final lecture or final problem solving session for Euler for rigid body rotation, I will apply Euler equations that I have talked about in earlier lectures to solve rigid body problems. You will see this is slightly more subtle, but you must learn it. So, the first problem that I take is a rectangle of sides A and B is rotating about one of its diagonals. So, what I am talking about is, here is a rectangle with sides A and B, and it is rotating about one of its diagonals like this, with angular speed omega. Find the torque needed to make it rotate like this. Okay. Now, this is rotating about a diagonal. So, it is not rotating about one of the principal axes. So, if I were to calculate L, the angular momentum, this has component L1 along the principal axis, L2 along the principal axis 2 plus L3 along principal axis 3. Let us make those principal axes. This let me take to be 1 at this position. The axis parallel to the long side, let me take that to be 2, and 1 cross 2, 3 at this position would be coming out. Now, L1 would be I1 omega 1. Now, if I take the angle out here of the diagonal with the axis 2 to be theta, then this is going to be equal to I1, which is about 1 m b square over 12, which is I1 times omega 1. Omega 1 is the component along 1, which is going to be omega sine of theta. Similarly, L2 is going to be I2 omega 2, which is going to be equal to m a square over 12 omega cosine of theta. So, along the way, let us also write, I have already calculated this, omega 1 is omega sine of theta, omega 2 is omega cosine of theta, and omega 3, which is the component of omega in the axis 3, no matter where the rectangle is, omega 3 is always going to be 0. This also tells you that omega 1 dot is 0, this tells you omega 2 dot is 0, and this tells you omega 3 dot anyway is 0, because omega 3 remains 0. Let us now apply Euler's equations to this. So, Euler's equations tell me that tau 1 is going to be I 1 omega 1 dot plus omega 2 omega 3 I 3 minus I 2. And we have already seen that omega 3 is 0, omega 1 dot is 0, and therefore, tau 1 is 0. Tau 2, that is the torque required in the direction of 2, is going to be I 2 omega 2 dot plus omega 3 omega 1 I 1 minus I 2, and we again see that omega 2 dot is 0, omega 3 is 0, and therefore, tau 2 is also 0. The only component that is non-zero is tau 3, which is I 3 omega 3 dot plus omega 1 omega 2 I 2 minus I 1. Omega 3 dot is anyway 0. So, the only term that contributes to the second term, and this is going to be omega sin theta times omega cosine of theta. I 2 is m a square over 12 minus m b square over 12. So, this comes out to be omega square sin theta cosine of theta m over 12 a square minus b square. Since we have taken a to be smaller than b, we get tau 3 to be equal to m omega square sin theta cosine of theta over 12 b square minus a square with a minus sign. That means it is in the negative 3 axis. So, let us make this again and interpret the result. This is the rectangle, it is rotating like this. This is the direction of omega. This is axis 1, this is axis 2, and this is 3. 3 is coming out. So, tau 3 is actually going in. So, tau 3 is minus m omega square sin theta cosine theta over 12 b square minus a square, and it is going in. If it is going in, what I should be doing to keep this rectangle rotating is create a torque by applying forces out here. So, I will apply a force in this direction on this side and a force in this direction in this side, equal forces, so that there is no net force on the system, center of mass remains where it is, but it does give me a torque going in. If the forces are applied at a distance d, then the amount of force will be equal to tau 3 over d, and you can easily calculate this. Let us see if this result is also consistent with whatever way we have been solving the problem earlier. So, earlier what we were doing is we were taking I 1 omega 1, I 2 omega 2, and calculating the horizontal component, right. So, L horizontal in that case would be I 1 omega 1, this angle out here being theta cosine of theta minus I 2 omega 2 sine of theta, which will come out to be m b square minus a square over 12 omega sine theta cosine of theta. This is LH in this direction, and as the rectangle rotates, it is going to go in. So, delta L is going to be LH times omega, which is m b square minus a square over 12 omega square sine theta cosine theta delta L over delta t going into the page, and that is equal to tau 3. So, you see we got the same answer with Euler's equations and traditionally the way we have been doing by taking LH, horizontal component of L, and then calculating its change. Both give you the same answer. It also gives you a practice about applying Euler's equations. The second problem is also similar, in which I have taken a disk which is rotating about an axis shown here by this straight line with omega like this pointing up. This is omega vector. The disk is not rotating about the symmetry axis, but is tilted so that its perpendicular is making an angle theta with the vertical. We want to find the torque required to keep the axis rotating like the disk rotating like this. So, the problem is a disk is rotating about a vertical axis with angular velocity omega. The axis of the disk makes an angle theta with the axis of rotation. So, the question is, find the torque required to keep the disk rotating like this using Euler's equations. So, solution: to apply Euler's equations, I first need to identify the principal axes. So, I am going to take axis 1 along one of the diameters, axis 2 along perpendicular to the disk, and therefore, axis 3 is going to be coming out of the page at this position. As the disk rotates, obviously these axes are rotating, but what remains the same is that omega 1, that is a component of omega along axis 1, is omega sine of theta, and this gives me omega 1 dot is equal to 0. Omega 2 is equal to omega cosine of theta, and this gives me omega 2 dot is equal to 0. Omega 3 always remains 0, and this implies omega 3 dot is also 0. In the same manner, I1 is the moment of inertia about one of the diameters, and this is going to be m r square by 4. I2 is the moment of inertia about the axis of the disk, and this is m r square by 2, and I3 is again moment of inertia about one of the diameters, and this is m r square by 4. Let us now apply Euler's equations. Euler's equations tell me that tau 1 is going to be equal to I 1 omega 1 dot plus omega 2 omega 3 I 3 minus I 1. Now, omega 1 dot is 0, omega 3 is 0, and therefore, this whole thing is 0. Tau 2 similarly is I 2 omega 2 dot plus omega 3 omega 1 I 1 minus I 3, and again omega 2 dot is 0 and omega 3 is 0, and therefore, this whole thing is 0. Tau 3 is I 3 omega 3 dot, this is also 0, plus omega 1 omega 2 I 2 minus I 1, and this gives me omega square sine theta cosine theta m r square by 2 minus m r square by 4, and therefore, the answer is omega square sine theta cosine theta m r square by 4. So, again if I interpret this, this was the disk at this position axis 3 is coming out, and the torque has to be in this direction with amount mr square omega square sin theta cosine theta by 4. If I need the torque in this direction, what I need to do is apply a force this way and a force this way. If I apply the forces symmetrically at a distance d, or even if they are asymmetric, it does not matter, equal forces will give no motion of the center of mass, but their amount to give a torque like this should be equal to mr square omega square sin theta cosine theta over 4d, and that is the answer. For the third problem, I first want to show you a picture. This is the picture of a mill taken at a place called Orchha in Madhya Pradesh, and what it does is it is used to mix and press upon the materials to make that mixture which is used to repair the palace out there. The mixture consists of mud and some dal and cement and things like those. But why I am showing this picture to you is, as this mill rotates, we will show you that it presses the mixture with force which is larger than in its own weight, and therefore, it becomes a very effective tool to do this mixture and grinding, and that is what we want to solve. So, this problem can be formulated as follows. Consider a grinding wheel of radius r and mass m. So, we will take a wheel of radius r and mass m. Its axle is of length L. So, let us take this length L and is pivoted at one end. Find the force with which the wheel presses the ground if it is pulled with speed v. So, what we are saying is, at the given position, the wheel is going into the page or coming out of the page, does not matter. Let us say it is going into the page with speed v, then we are claiming that this is going to press out here by little more force than its own weight. And why that happens is because of this. If this is going in, then the way it is rotating, the upper portion is going in, this portion is going into the board, and this is coming out, not the board, the screen, and therefore, it has a horizontal angular momentum LH. As the wheel rotates, LH is going to come out of the page, and therefore, there is a torque required which is coming out of the page. And to get this torque, I need a force which is larger. As this LH also rotates as the wheel rotates, it comes out of the plane of the screen, and therefore, there is a torque coming out of the plane of the screen, and that requires a force out here which I will call N, and this comes out to be larger than mg, as we will see in the problem. So, in the solution, first I will do it by calculating LH and then through Euler's equations. L horizontal is equal to 1/2 mr square, which is I, times omega, that is the rotational speed of the wheel, which is nothing but 1/2 mr square v over r, which comes out to be 1/2 mr v. The whole thing is rotating about this vertical axis by some omega. This omega vertical is nothing but the speed of the center of the wheel divided by L. So, this is going to be V over L, and therefore, dLh by dt is going to be omega times LH, which is nothing but V over L times 1/2 mr v, which is mr v square over 2 L. So, as this wheel rotates, if there is a force N and its own weight is mg, it requires a torque coming out, and for that I have to have N larger than mg. N minus mg times L, if I take this torque about this point O, which is a stationary point, it should be equal to the delta LH by delta T, which is nothing but equal to m r v square over 2 L. This implies N is going to be equal to m r v square over 2 L square plus mg. I should have used a capital M out here, which is the same. So, you see the normal reaction of the ground is larger. If the normal reaction of the ground is larger, that means the wheel also must be pressing it by that much force. So, wheel presses the ground by a force N equals mg plus mr v square over 2 L square, which I also can write as mg plus mr over 2 omega square. So, you see it helps in grinding. Now, as a result, what is going to happen if I were to take this whole thing assembly, it is not moving in vertical direction. This, so if I take this whole assembly N, this is having a force which is N, which is equal to mg plus some extra term, and the weight down here is mg. So, to keep it in balance, so that it does not move in the vertical direction, the pivot out here must be applying a force N minus mg at this point, and therefore, by Newton's third law, the pivot is going to be pulled up by this force N minus mg. So, with time it will tend to come out. So, this is on the side. Now, I want to solve this whole problem with the approach of Euler's equations. To solve the problem with the Euler's equations, we need to first identify the principal axes, see them rotating and take appropriate components. So, let me draw the wheel again. The wheel was like this, with the upper portion going in and the lower portion coming out. Let me now introduce the principal axis. Let me call this axis coming out as 1, and at this position of the wheel, when it is just about to enter the screen, let this axis be 2 along the diameter, and let the axis, therefore 1 cross 2 coming out of the plane of the screen be 3. So, these are my principal axes. As the wheel rotates, the axes are also going to rotate. Let me look at this whole thing from this side and make this wheel here. Then you see that axis 1 is coming out, axis 2 is up, and axis 3 is going to your left. So, 3 and 2 at this time. As the wheel rotates, as the wheel goes in, you will see that axis 3 and axis 2 will tend to rotate like this. So, if I make it after time t, after time t, what I am going to see is that the original axis 3 was like this, original axis 2 was like this, and now axis 2 has come here, axis 3 has gone here, and axis 1 remains coming out, and the wheel has rotated a bit. The omega vertical, which was v over L, is pointing in the original axis 2 direction, and omega with which the wheel is rotating about the horizontal axis is pointing away from the axis 1, which I will show in the upper left curve as this. This is omega. So, let us write these quantities. Omega 1 is equal to minus v over r, because it is pointing in the direction opposite to the direction of axis 1, and omega 1 dot is therefore 0. Omega 2 now is going to be time dependent, and since I will show the angle out here, this is omega t and this is omega t. Omega 2 is going to be equal to capital omega cosine of omega t, and omega 2 dot therefore is going to be equal to minus capital omega times omega sine of omega t. And similarly, omega 3 is going to be omega capital omega sine of small omega t, and omega 3 dot is going to be capital omega small omega cosine of omega t. Let me go to the next page and make this picture again. Here is this wheel, here are the original 3 and 2 with capital omega pointing in this direction. This is my axis 2, this is my axis 3, with this angle out here being omega t, and axis 1 is coming out. Omega 1 we have already said is minus v over r, omega 2 is capital omega cosine of omega t, and omega 3 is omega sine of omega t. How about I1, I2 and I3? I1 is 1/2 mr square, I2 is about diameter, so it is going to be 1/2 of 1/2 mr square. Since everything is symmetric, it is mr square by 4, and I3 is also mr square by 4. Now, I know that tau 1 is going to be, by Euler's equations, I1 omega 1 dot plus omega 2 omega 3 I3 minus I2. I3 and I2 are equal, and therefore, this term is 0. Omega 1 dot is 0. So, omega 1 or tau 1 comes out to be 0. How about tau 2? Tau 2 is going to be I2 omega 2 dot plus omega 3 omega 1 I1 minus I2, and this comes out to be I2 is mr square by 4 times omega 2 dot, which is minus capital omega omega sine of omega t, plus omega 3 omega 1, which is going to be minus v over r. Omega 3 is capital omega sine of omega t, and I1 minus I2 is mr square by 4. Since v over r is omega, we get this to be equal to minus m r square by 2 capital omega omega sine of omega t. That is my tau 2. So, the torque in this direction, I will make it again in the next screen, is equal to torque in direction 2 is in the opposite direction to 2, and it is equal to m r square by 2 capital omega omega sine of omega t. How about tau 3? So, let me make this picture again. I have the original 2 and 3, this is my axis 2, this is my axis 3, this is omega t, and we have already calculated that tau 2 is in this direction and its magnitude is mr square by 2 capital omega omega sine of omega t. Now, tau 3 is I 3 omega 3 dot plus omega 1 omega 2 times I 2 minus I 1, and this is equal to I 3 is again mr square by 4, and omega 3 is nothing but capital omega omega cosine of omega t plus omega 1, which is minus v over r, omega 2, which is capital omega cosine of omega t, and I 2 minus I 1 is minus mr square by 4, with v over r equal to omega, we get this again to be equal to mr square over 2 capital omega omega cosine of omega t. So, what we have here is that towards 3 I have m r square over 2 capital omega omega cosine of omega t. So, net torque is a combination of these two, and that is very easy to calculate. If you take the components in the vertical direction, if I take these components, they are going to cancel, because tau 2 vertical component is going to be equal to mr square over 2 capital omega omega sine of omega t, and this angle out here is again omega t cosine of omega t, and tau 3, which is going to be in the up direction, is going to be mr square over 2 capital omega omega cosine of omega t times sine of omega t, and therefore, these two terms cancel. What you are left with is the horizontal torque, which will be show that by this purple color, the net of these two is going to be in this direction, the original 3 direction, and its magnitude is going to be mr square. So, tau is going to be mr square over 2 capital omega omega cosine of omega t times cosine of omega t plus mr square over 2 capital omega omega sine of omega t times sine of omega t, which is nothing but equal to mr square over 2 capital omega omega cosine square omega t plus sine square omega t is 1. Again, if I play around, r omega is v, so I can write this as m r v capital omega over 2, capital omega is v over L, so I can write this as m r v square over 2 L, which is the same answer as obtained earlier. Let me now translate this back here to this wheel. At this position, this was the 3 axis 1, 2 and 3, and what we saw is that the torque is in this direction coming out of the screen all the time, no matter where I am, it will be coming out of the screen with the same calculation, and its value is tau equals m r v square over 2 L, same as we obtained earlier. So, I have the torque coming out, and to calculate the force I will again assume N and mg going down. Rest of the calculation is the same as I did earlier. We have gotten the right tau, right torque, and from that everything else follows. Why I did this problem is to show you that when you apply Euler's equations, you have to be careful in taking into account the fact that principal axes are also rotating, and therefore, omega becomes the component of the angular velocity becomes time dependent. Now, I will solve one more problem, the fourth problem, which is about the precession of a gyroscope, or the demo where I showed that if I take a bicycle wheel on an axle which is rotating and put it on a stand, it starts precessing, and we want to calculate that precessing velocity. The way we did it earlier was we said that let us say it is going like this, so that spin omega is coming into towards the base. Then it has an angular momentum L this way, and because there is a weight pulling it down mg, if I sit at this point, this mg provides a torque. What kind of a torque is it providing? It provides a torque, if you use the right hand rule, it provides a torque that is going in, and therefore, the L itself starts moving in that direction. The head of L will start going into the page, and because of that the wheel has to rotate, otherwise L will not change, right. So, the wheel will start coming out with a precession velocity omega. So, let us calculate this. I had done this earlier while showing the demonstration. I want to solve this using Euler's equations. And as we did in the previous problem, first thing I do is identify the principal axis. So, here it is, this is the wheel. So, let us make 1 going this way, 2 along the diameter, and therefore, 3 also comes along the diameter coming out of the page at this position. And if I look at it from this side, again what I am going to see is this wheel where 1 is coming out, 2 originally is like this going up, and 3 is going to the left. Since the wheel is rotating the way it has been shown with that bright green, it is rotating like this. So, after some time the 2 axis will move here and 3 axis will move here, making an angle omega t like this, and the wheel starts precessing. Let us take the precessing velocity to be omega p. I know I told you earlier that the wheel will be moving out, but omega p will come out to be negative if I take it like this. Now, if you notice that this omega, if this is at an angle theta from the vertical, omega p has a component along 1 which is omega precession cosine of theta, and a component along this original at this time along 2 as omega p sine theta. So, I have out here, I will show with green, I have omega precession as omega p sine theta, and therefore, I can write omega 1 as minus omega spin, right, omega 2 as omega p sine theta cosine of omega t, and omega 3 as minus omega p sine theta sine of omega t. We have identified omega 1, omega 2 and omega 3. I 1 is equal to I 0, which could be m r square by 2 or m r squared, I will just write it I 0, and I 2 equals I 3 because it is a symmetric wheel, and let us call this I. So, I have I 1, I 2, I 3, omega 1, omega 2, omega 3. So, let me write this again by making this picture. I have this bicycle wheel with the original 2 and 3 like this, 2, 3 original, 1 coming out. With time 2 goes like this and 3 like this, with this angle being omega t. Omega p sin theta is along the direction of original 2, and therefore, I have omega 1 which is minus omega. Oh, I should also add the component plus omega p cosine of theta. Let us see if it is in that direction. Yes, omega p cosine theta is indeed in the direction of positive 1. Omega 2, which we have written as omega p sin theta cosine of omega t, and omega 3, which is equal to omega p sin theta sine of omega t. I 1 I am taking to be I 0, I 2 equals I 3 equals I. Let us now write the torque equation. Tau 1 is equal to I 1 omega 1 dot plus omega 2 omega 3 I 3 minus I 2, and this whole thing comes out to be 0 because omega 1 dot is 0 and I 3 equals I 2. So, this is 0. Tau 2 is equal to I 2 omega 2 dot plus omega 3 omega 1 I 1 minus I 3, which is equal to I 2 is I, omega 2 dot is going to be minus omega p omega sine of theta sine of omega t plus omega 3, which is omega p sine theta times omega 1, and since omega p is very small, as we saw in experiment, I am going to take this as minus omega, times minus omega times I 1 minus I 3. I 1 is I 0 minus I. And what is tau 2? Let us see that. If I look at this picture which I made earlier and I make it again, here is mg, and about this point tau 2 is pointing in the direction opposite to current right now, whatever or the torque is pointing in the direction of 3 in this direction. This is tau, and how much is the magnitude? It is equal to m g l sin theta. So, if I were to calculate tau 2, tau 2 would be in this direction, and this is going to be minus m g l sin theta sine of omega t. Oh, for the omega 3 out here, I also had a sin omega t here, which I forgot, and it should be equal to minus I omega p omega sin theta sin omega t minus omega p omega sin theta I minus I 0 or I 0 minus I sin omega t. Let me write this again. So, I have minus m g l sin theta sin of omega t is equal to minus I omega p omega sin theta sin omega t minus I 0 minus I omega p omega sin theta sin of omega t. So, now I can cancel sin omega t from both sides. I can cancel sin theta from both sides, and this minus sign also goes away, and therefore, what I am left with is m g L is equal to I omega p omega plus I 0 minus I omega p omega. Now, this wheel by perpendicular axis theorem has, whether it is a wheel or a disc, has I 0 equals 2 I, and therefore, I 0 minus I is also I. So, we have m g L is equal to I, where I is the moment of inertia about a diameter, omega p omega times 2, and this immediately gives you that precession velocity omega p is equal to m g L over 2 omega. If I take this to be a wheel with mass only on the rim, then I would be mr square by 2, or there is an I here, and this gives me m g L over 2 omega times m r square by 2. This 2 cancels, m cancels, and I get omega p equals g L over omega r square. And that is the answer that we had gotten earlier also. So, again you see, while doing this problem, what we did was took explicit care of saying how the principal axes are rotating, and therefore, omega, the component along them, had a time dependence. I will leave it for you to get the same answer by considering tau 3 and writing tau 3 equals I 3 omega 3 dot. So, let me just write this. I will leave it for you to write tau 3, which is I 3 omega 3 dot plus omega 1 omega 2 I 2 minus I 1, and get the same answer. So, this completes our discussion on rigid body dynamics, with the final being solving the rigid body dynamics using the Euler equations.